So your second condition is work is done when we change the kinetic energy of an object. And kinetic energy, 1/2 mv squared, it's a derived formula. And this work shows you exactly what happens. I'm not going to talk you all the way through it, but using these three formulas, we can work our way down to here. And basically, delta of 1/2 mass times velocity squared, and that's the delta, that's the change in kinetic energy. And the conclusion here, when work is done to change an object's energy, and this is usually by changing its velocity. When this happens, the amount of work done equals the change in the object's kinetic energy. So where work is force times distance and kinetic energy is 1/2 times the mass times the square of the velocity. Example A, a 12 kilogram mass is at rest. How much work is done on it to increase its velocity to 5 meters per second? So the initial amount of kinetic energy is 0 because it is at rest. In order for an object to have kinetic energy, it has to have both mass and velocity. If velocity is 0, kinetic energy is 0. So here's basically what's going to happen. Here is the object. We are going to exert a force on the object, and we are going to continue to exert this force on the object. The object is accelerating at 5 meters per second. To 5 meters per second, excuse me. So find the final amount of kinetic energy. The formula, 1/2 times the mass times the velocity squared. The kinetic energy is 150 joules. Let's move this over. (150 kilograms times meter squared times divided by second squared is joules. Newton meters per joule. I'll redraw my picture here. There we go. So initially we had 0 kinetic energy, and at the end we had 150 joules of kinetic energy. So the change in kinetic energy is 150 joules. So the amount of work done is equal to the amount of kinetic energy, 150 joules. Example B, work is done on a 20 kilogram mass to increase its velocity from 3 meters per second to 5 meters per second in a time of 4 seconds. How much work is done? So here's the basis of what's happening. Here's my 20 kilogram mass. It's moving at 3 meters per second. The work is done on it, and then it's moving at 5 meters per second. Now, what we have to do here is we have to calculate the initial kinetic energy and calculate the final kinetic energy. So initially we have 1/2 times the mass, which is 20 kilograms, and the velocity is 3 meters per second. And we have to square that quantity. Go back up to the other example. I put the exponent inside. Should be on the outside. So the initial amount of kinetic energy is 90 joules. The final kinetic energy, 1/2 times the mass, which is still 20, and now the speed is 5 meters per second, quantity squared, and this is 250. Now, if you look over here, common misconception is that we could say 1/2 times 20 times the quantity of 5 minus 3 squared. 1/2 times 20, and this is 2 squared. 40. But this is wrong. It's not 40. We are about to calculate it. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy, 160 joules. Change in kinetic energy is 160 joules, so the work done is 160 joules. So notice that the amount of work done does not depend on how quickly we accelerate the object from 3 meters per second to 5 meters per second. The work just depends on how much the kinetic energy changed. So these examples reinforce our basic definition of work. Work is transforming energy from one form to another. And the amount of work done equals the amount of energy transformed.